Hello, today I am here to introduce my project OrbitWatch, a satellite collision risk intelligence platform. Our team members are Shubham Singh, Prachi Diswar, Shivani Singh, and me, Sarth Mishra. Our project has been successfully completed under the supervision of Dr. Vivek Kumar sir. First, we'll go over the abstract. The rapid increase in satellite constellations in the lower Earth orbit has significantly raised the probability of orbital collisions and space debris generation. OrbitWatch is a web based satellite collision risk intelligence platform developed to monitor satellites, detect conjunction risks, and provide maneuver recommendations using real time orbital data. The platform calculates collision risks, scores using missed distance, relative velocity, and time to closest approach parameters. It also provides real time 3D visualization using 3JS and satellite JS for smooth browser based rendering. The system fetches live Starlink TLE data from Celestrak and applies the SGP4 orbital propagation algorithm to compute accurate satellite positions and velocities. Now, we move over to the introduction. Satellite constellations such as Starlink, OneWeb, and Amazon Kuiper have increased the number of satellites in the Earth orbit dramatically. So, the question is, what is the importance of this topic? Well, high speed satellite collisions can generate thousands of debris fragments. Space debris may trigger cascading collisions known as Kessler syndrome. Continuous monitoring of orbital traffic is necessary for space safety. Well, what is the scope of this project? Development of a real time satellite monitoring and collision detection platform. Integration of SGP4 orbital propagation with live TLE data. Risk scoring and conjunction analysis using spatial algorithms. Real time 3D visualizations of satellites in a browser. Maneuver recommendation generation for high risk conjunctions. Next, we move on to the problem statement. The question is, satellite collision monitoring is becoming increasingly important due to the rapid growth of mega constellations in lower Earth orbit. What are the limitations of existing systems? Well, commercial space domain awareness tools are expensive, so costs are a big factor. Government conjunction data is restricted. Most of the data is confidential. Many platforms focus on only visualization without risk analysis. So there you go. These are some of the important limitations of the existing systems. What are the technical challenges? Efficient real-time processing of large satellite dataset, accurate propagation and constellation and conjunction prediction, real-time rendering of thousands of moving satellites, reliable collision risk scoring and alert generation. Well, what we propose is, there is a need for scalable web-based and cost-effective platform that combines live satellite tracking, conjunction detection, collision risk assessment, and maneuver recommendation using publicly available data. The objectives are to develop a real-time satellite collision monitoring platform using publicly available orbital data, to fetch and process live Starlink TLE and Celestrak automatically, to implement the SGP4 orbital propagator for accurate satellite collisions, to use KDT spatial indexing for efficient conjunction screening of more than 10,000 satellites, to compute collision risks, to generate maneuver recommendations, to design an interactive 3D visualization using interface, to provide a REST API endpoints for conjunction and satellite data access. Well, the existing systems and the literature review. Space domain awareness systems such as United States Space Surveillance Network (SSN) provide conjunction tracking services. Commercial tools like AGI, STK, and Leo Labs offer high fidelity collision analysis but require expensive subscriptions. Cellistack provides two-line element orbital datasets widely used in academic and research applications. Satellite JS enables browser-based SGP4 orbital propagation for web applications. 3JS provides WebGL powered real-time 3D visualization capabilities. Limitations are high operational cost, limited public accessibility, lack of integrated real-time visualization and risk scoring, no maneuver advisory support in many visualization platforms, scalability issues with large satellite datasets. The architecture is, first we have a data layer that fetches live data, then the computational layer uses AAP scheduler for periodic execution, applies SGP4 orbital propagation, then the API layer, and afterwards the front end layer. Well, this is a system architecture. Well, above at the top we have system. It breaks down into collect, analyzes, and generates. First, we move over to the collect section. It collects the satellite data, for example, satellite ID, orbital parameters, and velocity data. Afterwards, it analyzes the collected data, for example, collision risk, risk level, close approach, and afterwards, at the end, it generates optimization suggestions like where can the satellites move, how much space can be created, any ways to avoid their collision. Afterwards, the user can log in and access the logs. So there you go. Then the methodology is requirement analysis and project planning, collection of live TLE data from Cellistack, backend development, implementation of SGP4 KD tree based risk scoring, front visualization, and REST API. The tools used are Python Fast API, UVCon, database is SQLite, orbital propagation, Python SGP4, spatial indexing, SciP spatial KD3, front end 3JS, satellite JS, chart.js, scheduler, AP scheduler, IDE, Visual Studio Code. Hardware requirements are processor Intel Core i5 or equivalent, minimum 8 GB RAMs, minimum 1 GB disk free space, WebGL supported graphics card, and internet connection. Software requirements are Windows, Linux, or macOS, Fast API, Python 3.10 plus, SQLite 3, 3JS, satellite JS, chart.js, library, Python SGP4, AP scheduler, Visual Studio Code, Google Chrome. Well, this is the expected output. As you can see, the dots on the globe of in the screen in front of you are the satellites. The green and the red lines depict their trajectories and their orbital paths respectively. As you can see, when clicking on a particular dot, it depicts us the altitude it is on, the speed, inclination, RAAN, average of perigee, eccentricity, and the time period it has been since. And to the right you can see collision alerts. As you can see, the Starlink 32210 and 6370, their distance between them is 9.84 kilometers and relative velocity is 9.76 kilometers per hour. The risk factor is written below. It also presents analytics and other maneuvers. A total of 10,304 satellites as of now are available, and 5 of them are at critical risks. As you can see, this is the missed distance distribution. It depicts the satellites that is the distances between the satellites and the between the satellites and other factors. And to the right it depicts relative velocity distribution. As you can see, Starlink 32952 and Starlink 6214, their collision risk is high, and so on. Well, the applications are space safety, research and education, domain awareness, defense and security, visualization, and future commercial usage. Future enhancement are integration with official space track conjunction data, implementation of advanced probability of collision, time forward orbital simulation for future conjunction prediction, multiple constellation support using OneWeb and Amazon Kuiper, interactive maneuver simulation interface, geological orbital risk heat map visualization, email user authentication. Thank you.